If you want to measure the rocks hitting our planet, Earth is a scientifically terrible place to do it. Before a meteor reaches the ground, it hits the atmosphere. Small objects burn up entirely, and large ones fragment into pieces. Add in the daylight that washes out daytime impacts and the oceans that swallow physical evidence, and we are left relying on a geographically scattered network of human observers to look up and report what they see. That human reporting network recently produced a distinct signal. This chart maps data collected by the American Meteor Society, and it shows a massive 4.5 sigma spike in the frequency of giant fireballs occurring in the first quarter of 2026. A statistical deviation that large happens by random chance roughly once in every 17,000 observations. You might immediately suspect an observer bias, the result of more cameras existing today than a decade ago. But when researchers adjust the math to account for that infrastructure growth, the 4.5 sigma spike persists. People are reporting more massive fireballs because more massive fireballs are hitting the air. Because of our atmospheric filters and observer blind spots, Earth's ground data leaves us with an ambiguous picture. We know more rocks are burning up above us, but we cannot know for sure from the ground if the structural makeup of our cosmic neighborhood has actually shifted. To find proof, you need a detector with no atmosphere to burn things up, no oceans to hide the fragments, and no geographic bias. You need the moon. It is an independent 4-billion-year-old physical archive that preserves every single impact exactly as it arrives. On April 6, 2026, 4 human beings ended up occupying the absolute best vantage point to read that archive. The crew of the Artemis II mission, Commander Reed Wiseman, pilot Victor Glover, and mission specialists Christina Koch and Jeremy Hansen, were positioned directly behind the moon. They were there during a precise solar eclipse geometry. The moon completely blocked the Earth and the sun, plunging their spacecraft into absolute, unmediated darkness. Cut off from Earth entirely, the crew was sitting inside the most contrast-rich optical environment a human has ever occupied. During a 57-minute window of totality, the crew watched the lunar night side. Without any telescopic aid, they logged 6 distinct flashes of light on the surface below them, 6 rocks slamming into the regolith in under an hour. Ground telescopes regularly miss faint flickers, and Earth's atmosphere scrambles incoming data. But by sitting directly in the eclipse shadow and watching the lunar surface light up, these 4 astronauts provided an unfiltered, cross-validated observation of the exact same debris spike the American Meteor Society had been logging down on Earth. Seeing a flash of light on a gray rock from 140,000 miles away is a staggering physical feat for human vision. Even in the darkness of the eclipse, the lunar surface is faintly illuminated by Earthshine, meaning an impact flash has to overcome that background glow just to register in an astronaut's naked eye. To figure out how big those rocks actually were, physicists use a parameter called luminous efficiency, the precise fraction of a meteor's kinetic energy that successfully converts into visible light upon impact. Working backward from the visual threshold of human sight, those flashes were not caused by drifting pebbles. They were silent kiloton-class detonations. Each one carried the kinetic yield of a small nuclear weapon, excavating fresh craters in a fraction of a second. There is a geographic factor to acknowledge here. From their position behind the moon, the Artemis crew had a direct line of sight to the entire visible night side at once, exposing them to 7 to 10 times more surface area than any ground-based telescope can observe on a given night. But even after researchers divide the 6 impacts by that massive surface area advantage, the naked eye brightness requirement remains the limiting factor. The kinetic energy required to produce 6 distinct, visibly blinding flashes in 57 minutes points directly to an elevated debris environment that our baseline models do not predict. Individual space events usually have comfortable, isolated explanations, but the Artemis II observations sit in the center of a 72-hour window where multiple systems flashed warning signs at the exact same time. 3 days after the crew watched those kiloton impacts on the moon, a rock the size of a 6-story building, named Asteroid 2026 GD, passed right through the gap between Earth and the moon. It was a clean, tracked flyby, but it arrived precisely as the fireball rate peaked. During that exact same window, Earth-orbiting satellites logged a severe spike in electron flux, A high-speed stream of plasma from a solar coronal hole battered the near-Earth environment, exposing the unshielded Artemis crew to an elevated radiation dose. While these events occurred in the same window, solar plasma and rocky debris originate from entirely different sources. They travel through space by different mechanisms, and the radiation stream is a coincidence of timing. The terrestrial fireballs, the lunar flashes, and the house-sized asteroid, however, share a physical origin. When independent orbital sensors, terrestrial fireball databases, and 4 astronauts all log extreme rocky activity in the same window, the math strongly suggests a structural feature, a temporary dense wave of space debris swept through our system. The data from both the terrestrial fireball spike and the kiloton lunar impacts point to a highly specific size of debris. We are looking at rocks measuring somewhere between 1 and 20 meters in diameter. That precise measurement represents the most dangerous blind spot in planetary defense. Objects smaller than a meter burn up harmlessly. Objects larger than 100 meters are massive enough to be tracked easily by survey telescopes. But rocks in the 1 to 20 meter range are too small to reliably track, yet large enough to penetrate the atmosphere and unleash massive kinetic energy near the ground. In 2013, a 20-meter rock entered the atmosphere over Chelyabinsk, Russia. It was tracked 0 times by global monitoring infrastructure before it arrived, and the resulting shockwave tore through the city, shattering windows and injuring over 1,000 people. Go back further to 1908, and a slightly larger object flattened 2,000 square kilometers of Siberian forest during the Tunguska event. Devastating surprise impacts from untracked, mid-sized debris are an established, recurring feature of living in this solar system. The 6 craters the Artemis crew watched form on the Moon served as proof that this dangerous, untrackable blind spot is currently active and densely populated with debris. The scientific data collected behind the Moon is invaluable, but the 4 people who collected it are currently strapped into a capsule, preparing for the single most dangerous phase of their entire mission. Returning from lunar distance means the Orion capsule will hit Earth's atmosphere at Mach Bodhi 2, 10 times the speed of the fastest jet ever built. The air in front of the vehicle cannot get out of the way fast enough. It aggressively compresses, generating a fiery 6,000-degree plasma environment, hotter than the surface of the sun. During the uncrewed Artemis I test flight, the capsule's avcoat heat shield experienced a failure mode known as spallation. Instead of the material melting away smoothly to carry heat outward, intact chunks of the protective shield unexpectedly sheared off the spacecraft in a pattern engineers did not anticipate. To keep the Artemis II crew safe, NASA engineers scrapped the original return trajectory. They replaced the standard skip entry, which caused the thermal stress, with a direct, sustained plunge into the atmosphere. It is a logical solution that exists in computer models, but it has never once been tested with human lives on board. Humanity's only direct witnesses to our active wave in our planet's debris field are plunging through the atmosphere, trusting an unproven heat shield to survive the fall and bring their warning home.